Ladies, I'm only human.
Freeway by Activision.
Welcome to 8-Blit, a channel covering all the tips, tricks, and everything in between for programming your own games for the Atari 2600 from 1977. In this episode, we're racing the beam with precision timing in order to create an asymmetrical playfield and use that to create a two-player scoreboard. We utilize a 6502 processor flag to use binary-coded decimals to keep score, and we wrap it all up into the beginnings of a playable game, with full source code provided. That's all coming up on this episode of 8-Blit. This channel is supported by viewers like you. A huge thanks to all of our patrons that help keeping the intrepid spirit of Atari alive by donating a few dollars each month. You can help me produce more episodes like this one, where we dive deep into the inner workings of the Atari 2600 hardware, the 6502 processor, and assembly language programming. Discover all the details and how it ticks, and get access to all the information and resources you need to create Atari games. All contributions are greatly appreciated. Keeping score is all about enhancing a player's overall enjoyment of a game. It's one of the ways we can provide a reward mechanism for your players, much like achieving a goal or objective within the game. It introduces another challenge, motivation for you to top your previous record or beat your friends. In simple games like Pong, it could be the only reward mechanism in the entire game. Imagine removing the scoreboard from Pong. What are we left with? You know when you've missed a ball, but how many? How many did you miss versus your friend? Who was better? Are you getting better? Without a scoreboard, players will resolve to keep track of the score themselves, thus determining their own rules of the game. This could result in some difficulties. After all, we've all had that one friend who would keep changing the rules on us, so they always win. In this episode, we're going to focus on creating a scoreboard using the Playfield graphics. Much like classic games such as Pong, Combat, Asteroids, Space Invaders, and Breakout. Sounds easy, doesn't it? You may be surprised at the obstacles we'll need to clear in order to achieve our goal. We'll need to do a deep dive into how the Atari 2600's TIA chip works, and use some really precise timing in order to create an asymmetrical playfield for our scoreboards. But it will be worth it, because this technique will be super useful for creating interesting and elaborate non-symmetrical playfields in the future. This will also help you understand how to build multi-digit displays using the player graphic objects. We'll cover that in a future episode. So stick around because there's a ton of information packed into this episode. In order to build our scoreboard, we first need to get really intimate with how the playfield works and how the Atari 2600's television interface adapter draws the screen. We've touched on this in a previous episode, so I'll include a link in the episode's description. Let's zoom into a game and break down what's going on. We'll highlight the playfield pixels that make up our scoreboard and background. For now, we'll exaggerate the spaces between the pixels to make it a little clearer. You can see that the 5 and 0 match up with the playfield pixels, each using 3 columns of pixels for the digit and 5 segments in height. Segment isn't an actual measure of anything on the Atari 2600. I'm merely using the term to represent an abstract number of scan lines used for one line of the digit. It could be 1 scan line in height or more. It depends on how tall you want your digits. The width of each playfield pixel, however, cannot be changed. Let's break down the playfield even more. The entire playfield display on the Atari 2600 is 40 pixels wide. There's a split down the middle giving you a left side and a right side, with each side being 20 pixels. The registers that hold the graphics for the playfield are only 2.5 bytes, which is 20 bits. This means the TIA is only capable of storing enough graphics for a single side. The TIA uses these 20 bits again to draw the exact same thing on the opposite side of the screen. After drawing the left side of the screen, it can draw the right side using one of 2 different modes: as an exact copy of the left side, or reflected. For our purposes in this video, we're going to stick to the copy mode. Both sides of the playfield together make up the visible screen. Each side of the playfield is split into 3 different sections. These are the playfield registers that hold the graphics used to draw the playfield. PF0 is 4 pixels, PF1 is 8 pixels, and PF2 is also 8 pixels. In copy mode, the right side of the playfield would look like this, with PF0, PF1, and PF2 displayed in the same order as the left. In reflect mode, the 3 sections are reversed and the pixels within are also reversed, displaying PF2, PF1, and then PF0 as a mirror image of the left side, with all their graphics reversed as well. Let's switch back to the first mode, copy. What we have here is a representation of a single scanline being drawn from one side of the screen to the other. When this happens on a CRT television, it's actually a beam of electrons being fired at the back of the screen to illuminate phosphor beads, which form the pixels of your game. When it reaches the right side of the screen, the beam needs to be turned off and repositioned back on the left side of the screen in order to begin drawing the next scanline. The time it takes to do this, we call the horizontal blank. Nothing is drawn at this point, but we still need to account for this time in our scoreboard display code, and we'll need every cycle we can get. The diagram we're using here is based on one first created by Andrew Davey and posted on the Atari Age forums. This is a really great and useful diagram, and Andrew's original version also includes additional information such as the TIA and CPU timing. Let's break down exactly when each of these 3 registers is displayed on the screen and when they can be safely written. The 4-pixel PF0 is first displayed immediately after the horizontal blank, when the beam makes its way back to the start of the next scanline on the left side of the screen. In terms of how many machine cycles have elapsed since horizontal blank started, PF0 is displayed during cycle 22 through cycle 28. This is the time when the electron beam is actually drawing the contents of PF0. In order for the beam to have something to draw, PF0 needs to be populated first. Let's have a closer look at how that works by examining the timing of a typical load store routine. A load instruction with a memory offset value, like this one, uses 4 machine cycles to access the memory location, pull the graphic data, and in this example, store it into the accumulator. Once we have our graphic, we need to store it into the playfield register, which uses 3 machine cycles. The playfield registers are also buffered, in a sense, which takes an additional 2 TIA clocks, which is 2/3 of a machine cycle. However, in some Atari 2600 clone consoles, the TIA may not be as precise as the original, and could use an additional clock before writing to the playfield register. This means our buffer could be 1 machine cycle. When we refer to machine cycles, we're referencing the processor clock, in this case the 6502, or more specifically the 6507. The TIA has its own clock, which runs 3 times faster than the processor. So 1 machine cycle on the processor is equal to 3 TIA clocks. You can also refer to them as color clocks or even TIA cycles. I usually refer to the processor as machine cycles and the TIA as clocks. With the time it takes for the store instruction to execute, including the buffer time, this means the total time to safely write to the playfield register is 4 machine cycles. Since we know the PF0 graphic is displayed at cycle 22, we need to ensure the store operation is completed before that time, or the register may not display correctly, resulting in missing pixels or displaying pixels from a previous update. Likewise, if you update the playfield register prematurely, you can also experience unwanted pixels, or the lack of pixels. It's due to this concern that I prefer to think of the timing in terms of when it's safe to write to the playfield registers, rather than when the playfield registers are displayed. If we adjust our timing for safe numbers based on when to execute your store instruction, we now know that we must write to the PF0 register at cycle 18 at the latest, and can safely rewrite it at cycle 25. This means PF0 contains our new graphic data before it's drawn, and we don't overwrite the data until it's no longer displayed on the screen. Now that we can ensure PF0 is properly written, we need to take care of the other side of the screen, One caveat with asymmetrical playfields is that we need to update the playfield registers twice a scanline, on every scanline, even if the graphic is the same on the next scanline. We're using the same memory address for two different parts of the screen, and there's a good chance that the left side is not exactly the same as the right side. Otherwise, it wouldn't be asymmetrical. After cycle 25, we have a bit of time before PF0 is displayed on the screen for the second time at cycle 49 through 54. This time we're safe to write to PF0 on cycle 45 and can rewrite it for the next scan line at cycle 51. Now that we can write PF0, we need to slip in some time to write to the 8-pixel PF1 register. On the left side of the screen, PF1 is displayed between the 28th and 38th cycle, and can be safely written up to the 24th cycle and rewritten for the right side on the 35th cycle. The right side is displayed from cycle 54 through 65, and can be safely written up to cycle 50, and rewritten for it to be displayed next on the right side on cycle 62. Our last playfield register, PF2, is first displayed on the left side from cycle 38 through 49, and is safely written up to cycle 34 and rewritten at cycle 46. On the right side, it's displayed for the second time between cycles 65 and 76, and can be written by cycle 61 and rewritten for it to be displayed next on the right side on cycle 73. After cycle 76, we start the loop all over again with 22 machine cycles of horizontal blank before PF0 is displayed on the screen again. Now that we know the timing required to create a stable asymmetrical playfield, let's have a look at how we can implement this in some code. We'll start with a basic routine that displays a single number and work our way up to two-player scoreboard. After that, we'll have a look at a playable demo that makes use of what we've learned. Let's start by looking at how we're defining the graphics we'll use for the digits of our scoreboard. As we know from previous episodes, our graphics are generally stored in data tables made up of bytes. Each line of our graphic is 1 byte, and each of the 8 bits in the byte will each be 1 pixel. This particular file defines 16 hexadecimal digit graphics from 0 through F. If we have a close look at a portion of the table, you can see the bits are either 0 or 1. If the bit is 1, that means a pixel will be drawn on the screen. You can see here how the 1s define the shape of 2 6s. We're doubling up our digits in pairs because each individual digit is only 4 pixels wide, including a blank spacer bit to keep a separation between digits. All the graphics are stored in the same manner. As you can see, the graphic above is made up of 2 5 digits. At this point, you might be thinking our scoreboard is going to be lame if every number is a double digit. And you'd be right. Thankfully, we have some logical operators that can help us mix these up to give us 256 combinations of hexadecimal digits. By using the bitwise AND instruction, ANDing our graphic with 0F, we effectively place a mask over the second 5 and remove the first. We can do the same with the next graphic, but this time using F0 to mask the first digit and clearing the second. Now it's a simple matter to use the bitwise OR instruction to add the two graphics together to give us a combined graphic for 65. It takes a bit of juggling to make it work, but that's why there's a ton of example code for this episode, which we'll have a look at now. Later, we'll discuss how to do decimal arithmetic instead of being stuck with a hexadecimal scoreboard. We're going to build this simple screen, a single digit drawn in the second playfield register, PF1. In this example, we're not going to attempt an asymmetrical playfield until we have our score displaying correctly for the left side. There's a bit of work we need to do that's not immediately obvious. In our code, we're going to be working primarily with two variables, score, which will be the number displayed at the top of the screen, and digit index, which will be the offset position in our digits data table for the graphic we want to display. A third variable called temp will also be used several times throughout this code and in other examples. This variable will be used for different purposes to hold a value for a brief moment and is not dedicated to one single purpose. Now we come to our first hurdle. We have our score, which was hard-coded as 6, but we need to determine which index position in our graphic data table the 6-digit graphic starts. We know that each graphic is 5 bytes in height, so we just need to multiply our score of 6 by the height, which is easier said than done because the 6502 instruction set doesn't include a multiplication or division instruction. The closest we can get is the shift left and shift right instruction, which will either multiply by 2 or divide by 2 by shifting all of the bits over one position. First, we'll load our score into the accumulator. Since we're only going to be displaying a single digit in this example, we need to ensure that our score does not go above the maximum value we can display. In this case, our digits are hexadecimal, so F is the largest number we can display. All we need to do is mask the first nibble in the hexadecimal number with a bitwise AND instruction, and we'll be left with whatever digit was in the first nibble. Now we need to do our multiplication by 5 for our graphic index position. We do this by first copying our score into a temp variable. Then we use the shift left instruction to multiply our number by 2, and then again for a multiplication by 4. And finally we add the score we saved into our temp variable back into the accumulator, which brings this to a multiplication by 5, and in a final index position of 30, which we'll store into our digit index variable. Now we can display our digits graphic. First we load the digit index variable into the X register, and then load the first line of the graphic from the data table. As you will remember, the digit graphics hold 2 duplicate digits in each. We'll use our bitwise AND instructions to mask the first nibble, so we only have 1 digit. After a double sync, to ensure we start off at the beginning of a scan line, we'll store our score into the PF1 register. Since we're not attempting to have 2 different scores on each side of the screen, we don't have an asymmetrical playfield, and there's no need to change PF1. So we can initiate a couple more W syncs before moving on to the next line of the graphic. This will continue until we draw all 5 lines. As you can see, the score on each side of the screen is the same, because we didn't change the PF1 register. Each W sync used in the routine resulted in the scoreboard using 3 scan lines for each line of the digit, for a total height of 15 scan lines. Let's add a second digit to the left side of the screen and keep the right side blank. This time, we're going to use the value 3C for the score. Obviously, hexadecimal isn't the best use for the scoreboard, but it's great for debugging your code, which we'll switch to decimal later, so bear with me on this. Just like in the first example, we're using the same variables with one exception. Our digit index variable is now 2 bytes. We'll need that second byte because we're going to have 2 different digit indexes, one for the first nibble of the score and one for the second. When finding the index position for the first digit we want to display, it's basically doing the same thing. Mask off the nibble and then multiply by 5. However, for the second nibble, we have to shift everything over into the first nibble. We can do this by dividing our value by 16 with 4 bitwise shift left instructions, by taking the value after the first 2 left shifts and adding it to the result of the final 2 left shifts. It acts the same as multiplying the result by 5. This gives us the second of our digit indexes. Now it's time to create the graphics for our scoreboard. Again, the first part is basically the same as our first example. We load the graphic for the first nibble and mask it off and store it into a temp variable. Then we do the same for the second nibble. The only new part here is that we're going to use a bitwise OR instruction to OR the graphic we stored in temp with the graphic that's in the accumulator. This will combine the 2 graphics together, giving us a double-digit scoreboard. Our kernel loop is a little different here. We're actually not displaying anything in PF1 on the first loop. The time it takes to get the graphics and combine them brings us to a point where PF1 can no longer be written on the left side of the screen. So we use the first part of the loop to handle the right side of the screen by clearing out the PF1 register by setting it to 0. We then initiate WSync to bring us back to the left side of the screen, where we'll determine if we need to move on to the next line of the graphic or use the currently loaded line. If you remember, we're using 3 scan lines for each line of graphic. Now, all we have to do is write to the PF1 Playfield register. On the last scan line of our scoreboard, we need to clean up the right side of the screen again by setting the PF1 register to 0. Since this would have been handled in the first part of our kernel, that code's not going to be executed again because we've terminated the loop. At this point, it's only been a few machine cycles since we updated PF1 with the final scan lines graphic, so we're going to have to wait a bit before we can clear it out again. For this, we're using the sleep macro to burn 20 cycles. Then we set PF1 to 0. Let's move on to a real asymmetrical playfield with a 2-player scoreboard. The way this works is no different than the last 2 examples. While the first one demonstrated a single digit, the second expanded on that to show 2 digits. This one further expands on the concept to show 2 digits twice. This time, it's just a matter of cramming all this into a single scan line. Prior to the kernel where we're going to draw the scoreboard, we've already calculated the indexes to the graphic data for the 4 digits we're going to display. This kernel is a 2-line kernel, which means that for every loop in the kernel, we're going to output 2 scan lines. The scan lines are shown in the source code as dashed lines so we can easily keep track of them, one being split between the bottom and the top of the kernel loop, and the other executing in the middle. In this context, I think it's helpful to think of the middle scan line as the first scan line, and the top of the loop as the end of the second scan line, which is essentially front-loading the graphics to be displayed on the next scan line. We can see here where we're loading up the digits graphics for the left score, and then combining them together, exactly how we did it in the previous example. On the first scan line, we're simply writing the graphics to the PF1 register to display on the left side of the screen. After that, we're going to save the graphic to draw again on the second scan line. Then, we immediately load the digit graphics for the right side. But we can't update PF1 yet because it's still being drawn on the left side of the screen. We throw in a few no operation instructions to kill a little time until it's safe to update PF1. We save the graphic for the next scan line by storing it into another temporary variable, just like we did on the right side of the screen. On scan line 2, we're going to increase our digit graphic indexes in preparation for loading the next line of the graphic a bit further on. But we have these instructions mixed up a little just so we can conveniently fit them into the tight timings of the playfield. For the remainder of the loop, we're pulling the graphics we saved from the first scan line on the left side and writing them to PF1. Again, before we update PF1 for the right side, we need to wait until it's drawn on the left, so we burn some cycles before updating PF1. Then we continue to loop at the top and start loading the new graphics for the next scan line. This cycle continues until the scoreboard is drawn completely to the screen. Up until now, we've been using hexadecimal digits for our scoreboard. This is pretty handy when we're debugging and we want some visual feedback on the screen, but our players aren't going to appreciate us keeping score in base 16 hexadecimals. So let's switch these to base 10 decimals. For our score, we've been splitting the 8-bit byte containing our score into 2 4-bit nibbles, 1 nibble per digit, then using the value in each nibble to calculate the index to the graphic to use for that digit. This works well and we want to continue doing it this way. The problem with this approach is that the maximum value a single nibble can represent is 15, which is great to display digits 0 through F in hexadecimal. But with the decimal, we need the maximum value of each nibble to be limited to 9 for displaying digits 0 through 9. Lucky for us, the 6502 processor can help us out with this. We can use binary coded decimals by setting the decimal flag. This changes the way that arithmetic is performed on the 6502. In decimal mode, the binary coded decimal is the same until we go past 9. At that time, the first nibble rolls over to 0, and the second increases to 1. While in binary mode, the first nibble continues to increase to 10, and only rolls over past 15. You can set the decimal mode by using the SED instruction, and turn it off using the CLD instruction. And the mode works along with the add with carry and subtract with carry instructions. Unfortunately, it does not work with any of the increase or decrease instructions. Let's have a look at how this works in practice. and fast forward to the area of our example code where we increase the score. First, we set the decimal flag by using the SED instruction. Next, we clear the carry flag. This is necessary because we're going to use the add with carry instruction to increase the score due to the increase instructions not working with how we want in decimal mode. We'll do the same with the second score, and then use the clear decimal instruction to exit decimal mode. And that all comes together to look like this. This episode already has a decent amount of example code available to you, but let's not stop there. I've included a rough draft of a new game I call Purrballs. Many of the previous episodes have been leading up to this moment, as the game is made entirely with the example code provided with each episode. Future episodes will introduce new concepts which will be incorporated into the game, like paddle controllers and much more. We may also have mini episodes where we debug or add special features to the gameplay. Over time, we're going to refine this into a solid release. The full source code for Purrballs is available along with this episode's example on our GitHub page. Scorekeeping is a great way to add excitement to your games. It creates tension and introduces additional challenging aspects to your game, like breaking your personal record or beating your friend's score, each with their own reward mechanism that brings the players back to the game over and over again. With a few tricks up your sleeve, you can implement a scoreboard for your game that uses the Playfield graphics, which can require machine cycle level precision in order to produce a stable board. You can also use the board while debugging and choose to display certain values in a hexadecimal or decimal format. As a demonstration of a live scoreboard, we've introduced our project Purrballs, which we'll use again in future episodes where we'll keep refining the gameplay with each new concept we introduce. More episodes will be coming soon, so remember to subscribe if you haven't already done so. Remember that all the code for this episode is available from our GitHub. We'll provide a link in the episode description. That's all for now. Thanks for watching, and I'll catch you later.
Solar Fox! There are like millions of them, Solar Fox! Like, what are we gonna do?